Okay, in this video, let's continue the discussion about properties of rational functions, section 5.2. This time, let's try to find the horizontal or oblique asymptote of a rational function. Okay, uh, so there's a concept. If a rational function r of x is proper, what is a proper? Proper means, that is, if the degree of the numerator is less than the degree of the denominator. Then, okay, so this is the concept proper. A rational function is called proper if the top term, the top has less degree than the bottom. Okay, the degree of the numerator is less than the degree of the denominator. Then you remember that we have AND behavior. When x approaches infinity or negative infinity, we just consider the leading term. The leading term has less value, the less degree than the denominator actually will grow to infinity very, very fast, or faster than the numerator. So as x approaches infinity or x approaches negative infinity, the values of r of x approaches 0. Okay, so for example, you have x squared plus 2x squared, whatever, plus 3x plus 1 over 4x to 4 plus x cubed plus 1, something like this. When we talk about the behavior at infinity, when we talk about horizontal asymptote, okay, horizontal asymptote studies the behavior of the graph of function at infinity as x approaches infinity or negative infinity. As x approaches infinity or x approaches negative infinity or infinity, the numerator can be simplified as x squared. Remember that AND behavior. The denominator can be simplified to be approximated, not simplified, approximated to be the leading term 4x to 4. Then this moment you can do the cancellation. You will get numerator is x, no, there's no numerator. Numerator x squared cancelled with the denominator. 2 cancelled with 2 from 4. You will get 1 over x squared. And this term will approach 0 as x extremely large. So this is the idea why as x approaches infinity or negative infinity, this value will always approach 0, just because after you study the AND behavior, you see that only denominator has x. The numerator becomes a constant, and this denominator will grow to infinity, very, very large. So it makes this reciprocal very small. Okay, so that's the discussion for the proper rational function. Proper rational function. And here you have the definition. Okay, then the theorem is the following. If a rational function is proper, the line y equal to 0, this number y equal to 0 is a horizontal asymptote of its graph. Okay, so this is the horizontal asymptote of the graph. And you can have whatever example you like. For example, in the textbook, they provide the proper rational function as x minus 12 over 4x squared plus x plus 1. And this is a proper rational function because the degree of the denominator is 2, degree of the numerator is 1. So the degree of the numerator is strictly less than the degree of the denominator. R of x is proper. Then, by the theorem, y equal to 0 is a horizontal asymptote. It's a horizontal asymptote. Okay? So that's the first case. Of course, after we get proper, we will have the counterpart, improper. Okay, so if the degree of the numerator is greater than or equal to the degree of the denominator, R is called improper. R is called improper. Okay? Proper, less than, improper, greater than or equal to. It can be equal. Equal is not proper. Equal is also included in the improper case. When you have an improper case, remember, we have the quotient of the polynomial functions. So this rational function is p of x over q of x. Then by the long division or by the syntactic division, whatever division you are familiar, you have the quotient plus the remainder over the denominator. Okay, the quotient plus the remainder over the denominator. And after the long division, the result is that the degree of R of x, the degree of this numerator, is less than the degree of q of x. It's one of the requirement. If the degree of remainder is greater than or equal to the degree of the quotient, you will continue the division, right? So it means by the long division, we write an improper rational function as the sum of a polynomial fx and a proper rational function. Okay, so this is a proper rational function because a degree satisfies the definition. This is a polynomial. And proper rational function will have value 0, approach 0. R of x over Q of x approaches 0 as x approaches infinity or x approaches negative infinity. So this term, when x is huge, you can ignore it. So the original rational function is more or less the polynomial as x approaches infinity or x approaches negative infinity, just because this proper part will be extremely small, can be ignored. Okay, so let's check the cases. Case 1, if f(x), this quotient is a constant, after long division, if you get a constant, the line y equal to this constant is a horizontal asymptote. Okay, if you get a constant number as a quotient, then it's a horizontal asymptote. If your function is a linear function, ax plus b, the line y equal to ax plus b is an oblique asymptote. It becomes an oblique asymptote. And in whatever case, in all other cases, the graph of r of x approaches the graph of fx as x approaches infinity or x approaches negative infinity. So basically these two functions can be approximated, can be approximately equal. Okay, so that's the improper case. In the improper case, you will have a horizontal. You possibly will have a horizontal asymptote, or the oblique asymptote, or you may not have an asymptote. You have some other graphs. Asymptote, normally so far we consider them as straight lines. Okay, let's see the example. For example, let's check. We have this rational function as a 3x to 4 minus x squared over x cubed minus x squared and plus 1. It's improper because the degree of numerator is 4, degree denominator is 3. It's improper. So we need the long division. Remember that if you have some missing powers, you just put 0 as a coefficient. And this is x cubed minus x squared plus 1. And then you divide the leading term by leading term. So 3x to 4 over x cubed is the 3x. 3x, you put a 3x on top of an x term. Then you do multiplication. 3x times x cubed, 3x to 4. 3x times x squared minus 3x cubed. 3x times 1 is plus 3x. And then you do subtraction. This term disappear. Here 0 minus negative 3. And this term you copy it. And here is a minus 3x. It's a subtraction, always subtraction. And then you divide the leading term by leading term. 3x cubed over x cubed is equal to 3. So plus 3. Okay, plus 3. Well, let's do the computation. 3 times x cubed. 3 times x squared. 3 times 1. This term 0, this term is 2x squared minus 3x and minus 3. Yes, okay, so we got this remainder and quotient. So h of x is equal to 3x plus 3 and plus this remainder 2x squared minus 3x minus 3 over x cubed minus x squared and plus 1. This is a linear function. This is a proper function, rational function. The original one is improper. And then here you have a linear function, then the y equal to 3x plus 3 is an oblique asymptote. Oblique asymptote, because this is proper. Proper one will approach 0 eventually, so this term you ignore it, you will get the first linear part. Okay, so this is a oblique asymptote. Second example. If we have 8x squared minus x plus 2, 4x squared minus 1. This is still an improper rational function because the degree of the numerator is equal to the degree of the denominator. Equal case is also included in the improper rational function. Okay, now let's do you divide the leading term by the leading term, you get 2. So you put 2 on top of a constant term. So 2 times all the terms, you will get a negative x. Here 0, here 0. So now you get a negative x. Negative x has degree less than the denominator. You stop. So the original rational function is equal to 2 plus negative x over 4x squared and minus 1. Okay? And this is a proper rational function. It will approach 0. And 2 is a constant number. So y equal to 2 is a horizontal asymptote. Okay, it's a horizontal asymptote. And you will actually observe that if the degree of the numerator is greater than the degree of the denominator by 1, if the difference is 1, you will have oblique asymptote. If the degree of the numerator is equal to the degree of the denominator, they share the same degree, then it will have a horizontal asymptote. Okay, same degree, horizontal asymptote. Greater than 1, the degree is greater than 1, you have oblique asymptote. Let's see if you have bigger difference. Assume this. Rational function is 2x to 5 minus x cubed plus 2 over x cubed minus 1. Now this difference of degrees is 2. Or let's try to do the division. Just be careful when you divide the dividend by the divisor, you have to add the missing term. Divisor, you don't need to do that. Okay, and then you divide the leading term by leading term, 2x squared. So you put 2x squared here. Then you do product minus 2x squared. Okay, this term is 0. This is 0. This is 0. Here is a negative x cubed plus 2x squared plus 0x plus 2. and you do the division, leading term by leading term. It's -1. So you minus 1. So -1 times x cubed, -1 times -1. So it's 2x squared and plus 1. This is difference, so it's 2x squared plus 1. So the g of x is equal to 2x squared minus 1. This is from the top. And plus 2x squared and plus 1 over x cubed minus 1. Okay? And this is a proper rational function. So as x approaches infinity, or x approaches negative infinity, 2x squared plus 1 over x cubed minus 1 approaches 0. It's a proper one. Proper one always approaches 0 at infinity and negative infinity. Then the graph of g of x approaches the graph of 2x squared minus 1. So basically you will see that the graph of g of x at infinity will be more or less like 2x squared minus 1, a parabola. Okay, so that's the idea. And in this case, we will not call it the asymptote. We just state those two graphs will be very close, right? So asymptote in the current textbook, it just means the straight lines, either horizontal or vertical or oblique. Okay. Okay, so there is a summary on page 350. Actually, that's what we had here. We had those. Let me see. Yeah, we had those 3 examples. The example you have oblique asymptote because the difference of the degrees is 1. This part you have horizontal asymptote because they have the same degrees. This part you have other case because the difference of degrees is 2. It's greater than 1. If it's greater than 1, you don't have a horizontal or oblique asymptote. But anyway, you're going to do the long division in order to determine this term. Okay, and when you do the long division, don't forget insert the missing term. Okay, so this is section 5.2. In the 5.2, we studied the basic properties of rational functions, and in the next section, we're going to try to graph rational functions. Rational functions is a quotient of 2 polynomial functions. Naturally, its graph will be harder than the graph of polynomial functions because you have to consider 2 polynomial functions and their interactions. Okay, so we will see the graph of a rational function in the next section. Okay, so we finish this video and we will start another video. Okay, do exercise, ask me questions. Bye bye.